Imagine we had a time machine, a vessel capable of traveling into the distant past without limits. We could journey back to the very dawn of our universe, though that might not be the most hospitable destination. A trip 1 billion years into Earth's past, however, would be an extraordinary adventure. It would allow us to witness our planet in its youth, to see what it was truly like so long ago. Preparing for such an expedition would require careful planning. We would need to pack a host of tools and equipment essential for scientific research and basic survival in an ancient, unfamiliar world. On this journey into the deep past, there is one thing that would be utterly useless: our modern knowledge of geography. All the maps, atlases, satellite images would be completely irrelevant. The Earth of 1 billion years ago looked nothing like the planet we know. The continents we are familiar with, Africa, Asia, the Americas, simply did not exist in their current forms. The very outlines of the land were alien and strange. In fact, during that remote era, it is highly probable that all the world's land was fused together into one immense supercontinent. This supercontinent was not the famous Pangaea, the one many of us remember learning about in school. Pangaea is a relatively recent feature in Earth's long history. The landmass that existed 1 billion years ago was something else entirely, an earlier and more mysterious world. This naturally leads to a compelling question. How can we possibly know this? Scientists do not possess a time machine to fly back and chart the planet's ancient geography. There is no direct way to observe Earth as it was in such a distant epoch. We must acknowledge that we cannot know with absolute 100% certainty what Earth looked like 1 billion years ago. To truly understand what makes a supercontinent super, we must first look at the fundamental materials they are made of. The solid surface of our planet, the crust, is not uniform. It comes in two distinct types: oceanic crust, continental crust. These are the building blocks of the lithospheric plates, but they have very different properties. Oceanic crust, which forms the floor of our vast oceans, is relatively thin. It typically measures only about 6 to 10 kilometers from top to bottom. It is also dense, composed primarily of dark, heavy volcanic rocks like basalt. Continental crust, on the other hand, is the material that rises above sea level to form the land we live on. It is significantly thicker than its oceanic counterpart, ranging from 20 to 70 kilometers in depth. This crust is also less dense, made up of lighter rocks such as granite. This difference in density is crucial. It is the reason continents float higher on the underlying mantle than the oceanic crust does. Think of it like a block of wood and a block of iron in water. The less dense wood floats high, while the denser iron sinks low. This simple principle of buoyancy governs the very structure of our planet's surface. This difference in properties leads to another fascinating consequence: a vast disparity in age. The Earth's surface is constantly being renewed through the process of plate tectonics. In zones of subduction, where one plate slides beneath another, crust is pulled down into the mantle and recycled. In zones of seafloor spreading, new crust is formed as molten rock rises to the surface and solidifies. This cycle of destruction and creation means that the Earth's surface is much younger than the planet itself. However, this renewal process does not affect both types of crust equally, leading to a dramatic age gap. Because oceanic crust is denser, it is almost always the one that gets forced down into the mantle when it collides with continental crust. The buoyant continents, meanwhile, tend to resist subduction and remain on the surface. As a result, oceanic crust is perpetually recycled and is therefore relatively young in geological terms. The oldest sections of the ocean floor are only about 200 million years old. Continental crust, however, can survive for billions of years. Within the hearts of modern continents lie ancient, stable cores known as cratons. These are time capsules, preserving rocks that can be over 4 billion years old, offering us a direct link to Earth's deep past. The modern theory that explains the movement of these crustal pieces is called plate tectonics. It provides the mechanism that Alfred Wegener's earlier theory of continental drift was missing. We now understand that the Earth's rigid outer layer, the lithosphere, is not a single solid shell. Instead, it is broken into several large plates. Numerous smaller plates exist too. These plates are not static, they are in constant slow motion. They float on a hotter, more pliable layer of the upper mantle called the asthenosphere. This layer acts like a lubricant, allowing the plates above to slide. The primary engine driving this movement is mantle convection. Deep within the Earth, rock near the hot core heats up, becomes less dense, and slowly rises. Near the surface, it cools, becomes denser, and sinks back down. This continuous circular flow, over immense timescales of millions of years, exerts a powerful drag on the lithospheric plates above, pushing and pulling them across the planet's surface. The concept of the supercontinent cycle began with the first one we identified, Pangaea. The name, coined by Alfred Wegener, comes from ancient Greek, meaning all earth. The most obvious clue is the jigsaw puzzle fit of the continents. The coastlines of West Africa, Eastern South America, match up with remarkable precision. Consider the submerged continental shelves. Beyond coastlines, the fossil record provides compelling biological evidence. Paleontologists have found identical land plants and animals from the same time period on continents now separated by oceans. For example, fossils of the small reptile Mesosaurus are found only in specific regions of South America, Southern Africa. Mesosaurus was freshwater and couldn't have swum across the Atlantic. Section 5. Looking to the future. The next supercontinent. The supercontinent cycle did not end with the breakup of Pangaea. The same tectonic forces are still at work today, pushing and pulling continents across the globe. By tracking plate direction and speed, scientists project movements millions of years forward. Models vary, but geologists broadly agree the continents will collide again. In roughly 200 to 250 million years, they will likely merge into a supercontinent. Scientists propose several scenarios. One model, called Pangea Proxima, suggests the Atlantic Ocean will stop widening and begin to close, bringing the Americas back into collision with Africa and Eurasia. Another scenario, Novopangaea, predicts the Pacific Ocean will close instead, causing the Americas to crash into Asia. The art of planetary reconstruction. Reconstructing the geography of a planet from billions of years ago is an incredibly complex task, a scientific endeavor that blends meticulous data collection with interpretive artistry. The process, known as plate reconstruction, aims to wind back the clock on plate tectonics, moving continents from their present positions to their ancient locations. For recent periods, like the time of Pangaea, the task is more straightforward. Geologists can use the magnetic stripes on the ocean floor, bands of rock with alternating magnetic polarity. The primary tools for this deep-time reconstruction are paleomagnetism and geology. By taking samples of ancient rocks from different continents and determining their age through radiometric dating, scientists can then measure their locked-in magnetic signature. This reveals the paleolatitude, the north-south position of that rock when it formed. By collecting enough data points from rocks of the same age on different continents, geologists can test whether those continents were clustered together at a similar latitude. Section 5. The rhythm of a planet. The sequence of Columbia, Rodinia, and Pangaea, spaced hundreds of millions of years apart, strongly suggests a recurring pattern in Earth's history, the supercontinent cycle. This grand rhythm dictates continents aren't destined to drift aimlessly. Instead, they follow a cyclical path of convergence, collision, and eventual dispersal. One full cycle lasts roughly 400 to 800 million years. This cycle is the planet's pulse, driving changes from climate to evolution. Assembly can happen two ways. Introversion, continents reverse and close the internal ocean to reassemble. Extroversion, continents traverse the globe and close the external superocean. This cycle frames Earth's long-term climate history. Assemblies often align with major ice ages, snowball Earth events. Mountain building increases rock weathering, drawing down CO2 and cooling the planet. Breakup often triggers intense volcanism, releasing greenhouse gases and warming. Our journey through deep time reveals a planet that is anything but static. The ground beneath our feet, which feels so solid and permanent, is in a state of perpetual, albeit imperceptibly slow, motion. We have seen how the theory of plate tectonics provides a powerful and elegant framework for understanding this planetary restlessness. It is the grand unifying theory of geology explaining everything from the violence of earthquakes and volcanoes to the majestic rise of mountain ranges. Most profoundly, it is the engine that drives the supercontinent cycle, the immense recurring rhythm of continental assembly and dispersal that has defined our planet's history for billions of years, and will continue to define its distant future. The evidence for this cycle is compelling and multifaceted. It began with the simple observation of a jigsaw puzzle fit between continents, an idea that grew from a curious speculation into a robust scientific fact. This grand cycle underscores the interconnectedness of all Earth's systems. This epic narrative, written in the language of rocks and time, is a humbling and awe-inspiring reminder of our small place within the vast and magnificent history of our ever-changing home.